So we're going to look at proof by induction, which is a method of proving something about the natural numbers. And I always like to say that actually it's not really a method of proof. It's not a trick. It's actually just the definition of the natural numbers. So the way that you define the natural numbers rigorously is you say, well, there's some number in there that we're going to call 1, and the rest of them are all going to come about because once I know that some number is in there, whatever it is, there's always going to be another one that's bigger than it that I can think of by adding 1. And it has to be the smallest set that has that property. So it's infinite, but it's just the smallest type of infinite that you can get. Actually, proof by induction is just using that property. So proof by induction. So the natural numbers n are defined as there's a number 1 in the natural numbers, and whenever k is in the natural numbers, there's another number, k plus 1, is in the natural numbers too. And there's nothing else. Okay, so that's what I've written down there basically is what are known as the piano axioms. Written down by somebody who, I think around the beginning of the 19th century. And it caused a lot of problems because people wanted to know, well, if I've got a system of set theory that can capture this quality, then can I at least prove it's consistent and things? And so you get Gödel's incompleteness theorem. That's a whole story that we're not going into. What I want to do is just show you how this can be used to prove some things. Therefore, if we want to prove something about the natural numbers, say some statement P of n, then we need to show, so we want to say that P of n is true for all n in n. Then we need to show P of 1, certainly. And we need to show whenever P is true for k, then it's true for k plus 1. Okay, so this is usually called the basis for induction. Oh, well, I won't imagine the ON there. And this is called the inductive hypothesis. It's a hypothesis because it's assume that something is true for k. And then the inductive step, so this implication, is the inductive step. And often people like to think of this as being like a set of dominoes. So if you have all sorts of wonderful YouTube videos of people showing dominoes falling down when they're placed sufficiently close to each other. The idea is, if I can show that the first one goes down, so if P of 1 falls, if this is the first one, if this falls, and I know that they're close enough together that whenever P of K is true, so whenever the kth domino falls, that the next one's going to as well, because they're all close enough together, then that's all I need to know, because the first one will go down and then they'll all go down in order. So this is the inductive step here. If kth falls, then k plus 1 falls. Okay, so that's the basic idea. Again, just seeing examples is kind of the best thing. And so example 1, that's just going to be the most the sort of favourite example that everyone sees when they do this for the first time. So I want to give a formula for what the sum of the first n natural numbers is. So the sum of the first n natural numbers is n times n plus 1 over 2. So in other words, if I do, so I'll just say, I'll write it like this. S of n is going to be the statement that 1 plus 2 plus 3 plus blah 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 plus n, this is equal to n plus 1 over 2. Okay, so basis for induction, and this is the proof. The basis for induction is to do this when n is 1. Well, then what does this say? This says that S of 1 is just the only thing that I get on the left hand side. So this is S of 1 is just going to be 1 on the left hand side equals what happens when I plug in 1 into the right hand side. Well, I get 1 times 2 divided by 2. But 2 divided by 2 is just 1. Correct. Good. So now I take the inductive hypothesis, which is that we assume S of k is true. And then we have to try and prove that S of k plus 1 is true as well. So let's just see what we get if we write down S of k. So i.e. 1 plus 2 plus 3 all the way up to k. This is equal to k times k plus 1 over 2. Okay, so we're assuming that, and now we have to see how we can prove that S of k plus 1 is true. Okay, so what I want to do is take this thing that I've assumed and modify it in some way so that I can say something about sk plus 1. So if I want to say something about sk plus 1, this sum needs to go all the way up, not just to k, but to k plus 1. And I can modify this equation if I add k plus 1 to both sides, and then it's going to start to look like what I want. So now we want to prove, so I want to use this sk plus 1. So let's add k plus 1 to both sides. And I get 1 plus 2 plus 3 all the way up to k plus 1. This is equal to k times k plus 1 over 2 plus k plus 1. Right. So now I want to modify the right-hand side so it ends up looking like what I want it to look like when n is k plus 1. So it needs to look like this fraction, so I need to put everything over a common factor of 2, and then I can start to manipulate this. So this is going to be equal to k, and let's just expand this while we're at it. So I'll write this as k squared plus k over 2, and then I can make this over 2, and then I can put that one over there as well. Right, good. So now let's try and think of how to factorize this so that we can get the answer that we're looking for. So I'll expand it out. I get k squared plus 3k plus 2 over 2. And this is a quadratic that you can try and factorize just by guessing, really, but I'm sure you've all seen it before, so you'd probably be able to guess that that's what you have to do. Okay, well, what have I just written down? I've just written down that the sum of the k plus 1, first k plus 1 natural numbers is equal to the fraction that I was looking for. So in other words, what happens when I take this and I substitute in k plus 1? So it's exactly the right thing. Hence, s of k plus 1 is true. Okay, so I've got s of 1 and s of k. Whenever that's true, s of k plus 1 is true. So s is true for all the natural numbers. So we're done. Okay, let's do another example. So there's example 2, going to be a very similar one. I'm just going to add up all the odd natural numbers, and we're going to discover that we get squares. So this is going to be, let's just call it P. So prove P of n, which is 1 plus 3 plus all the way up to 2 times n minus 1. This is equal to n squared. So I add up all the odd natural numbers until I get to this one, and I want that to be n squared. It's actually easy to sort of see why this is true if you think about it, because if you start with one odd, the first odd number is 1, and then you add the next odd number, that's 3, and then you add the next odd number, that's 5, you can see that you are going to get a square in each case. So kind of easy to see it from that, but we're actually going to prove it by induction. So the proof, P of 1, we have to start with the basis of induction. What do I get on the left-hand side? Well, I'm adding up from 1 all the way up to 2 times 1 minus 1. Well, that's adding up from 1 to 1. So there's only one thing on the left-hand side. And that is equal to 1 squared. It's true. Okay. Assume P of k. What's that? That's saying that 1 plus 3 all the way up to 2k minus 1. That's equal to k squared. Okay. Now I need to prove from this that that this will also work for pk plus 1. So again, I need to think, how can I modify the left-hand side so it looks like what I want it to? Well, I just need to add the next odd number in. So the next odd number after 2k minus 1 is 2 more than it, so it's 2k plus 1. So if I just add 2k plus 1 to both sides, then maybe I'll get somewhere. So adding 2k plus 1 to both sides, I get 1 plus 3 plus dots plus 2k minus 1 plus 2k plus 1 is equal to k squared plus 2k plus 1. So this left-hand side is exactly what it should be. And the right-hand side, well, that factorizes nicely, doesn't it? We've all seen that before. It's equal to k plus 1 all squared. But I've now just written down exactly what I wanted to. I wanted to write down the statement that the sum of the first k plus 1 odd numbers is equal to k plus 1 all squared. And that's what I've done. So hence pk plus 1 is true. And then we can just conclude by saying P1 and P k implies P k plus 1. These are both true, and hence the statement is true by induction. Okay, and then we'll see some more examples in the tutorials.